Namaste and a warm welcome to this lecture on mathematical foundations for machine learning. In the last couple of classes we have been looking at the idea of random variables. We looked at what a random variable is, like how do we characterize random variables. We said we have discrete random variables, continuous random variables and all those things. We characterize discrete random variable using the probability mass function, the continuous random variable to be the to be described by the probability density function, and we said that these are exact representation of the probability distribution. And in case where we do not have it, we talk about the cumulative distribution function. And then we said that okay, of all these things we still want one typical number which could probably characterize, say suppose I do not have the distribution information at all, like is there a typical number which would characterize this random variable. We took the example of the cumulative grade point average that students have, which is going to capture the performance of the students in a set of exams over his academic tenure. So we have we looked at the expected value of x, and we said that this expected value of x could yeah, it is a typical value indeed about the random variable, but it does not give much of an information. It does not give much of an information in the sense like okay, at some point of time I would have done really well, and at some point of time I would have done really bad, and but then it kind of evens out and then say look, the CGPA is like this. So it does not really capture the individual semester wise performance or whatever that is. So we wanted another measure, or we want another quantity which could be used along with the expected value of x or the mean, which could actually capture most of the information about the random variable. And in that process we looked at we said that okay, we want to look at the spread of the random variable. So we said that okay, look, we are going to have the variance that comes into picture. So before we get into the idea of variance, we will also discuss something called as the raw moments, or the moments about the origin, and then we will go about discussing the moments about the mean, and then we will get to the idea of variance. And in fact we must also remember that we saw that in the case of mean, this was the best approximate for the random variable, which was minimizing the squared error between the observed value and right, and basically you had the value x, random variable x, and we might look at one typical value which would best approximate. So we said that expected value of x was going to do the job, right, which is going to minimize the squared error between the observed value and the actual value, right. So we had that. Now what we are going to do is we are going to generalize this ideas of E of x to what we call as the raw moments, or the first case that we are going to look at is moments about the origin. Instead of just looking at E of x, we could actually look at expected value of x power n. So that is where we are going to look at the nth moment of the random variable. It has connotations to your physics that we study, like we studied moment of inertia and center of mass and all those things. So along the side we are going to look at these raw moments, right. So I am going to look at raw moments. I am going to write this as expected value of, let us say x minus say some c, the whole power n, which is nothing but sigma. Suppose if I take it to be discrete random variable, so this is going to be nothing but xi into it is basically xi minus c, the whole power n, into p of px of xi, the probability mass function. Let us say I is equal to 1 to say some capital N. And in case of the continuous random variable, this is going to look with this integration. So I am going to say this is going to be minus infinity to infinity, this is going to be x minus c, the whole power k, fx of x, or this is basically n. So x minus c, the whole power n, fx of x dx, right. This is what we are going to call as the nth moment. These are nothing but the nth raw moment about, let us say non-random value, or about I will take it as about a non-random value C. Right. So, this is what is called as the nth raw moment about the non-random value C, right. Now, suppose if I put C is equal to 0, suppose let C be equal to 0, in which case I am going to get expected value of x power n, which is nothing but sigma I is equal to 1 to n x I power n x I power n p x of x I for the discrete case, and for the continuous case this is going to be minus infinity to infinity x power n f x of x dx. So, when you set C is equal to 0, all the moments that we get, these are called as the moments about the origin. So, E of x power n is basically called the nth moment about the origin, nth moment about the origin. Right. This is what we call as nth moment about the origin. Now, the next thing that we look at is, let us look at this, suppose. So, therefore, the nth moment about the origin, so the first moment about the origin, the first moment about the origin is basically E of x power 1, which is nothing but sigma x I p x of x I, let us say I is equal to 1 to n, or integral minus infinity to infinity x f x of x dx, where f x of dx f x of x is basically the probability mass density function, and we are going to get this, the first moment about the origin is basically what we call as the mean mu, right, mean mu x. This is what we call as mean mu x. Now, we already saw that the expected value operator is basically a linear operator. That means, if we say that I have E of, let us say a x plus b y, it is nothing but for scalars a and b, for scalars a and b we have E of x plus b y is nothing but a times E of x plus b times E of y. We will keep it this way for some, this is the linearity of the expected value operator. Now, what I am going to do is I am going to use this for some in other place, which I am going to do in a couple of minutes from now. Okay. So, now I understand that the first moment about the origin is basically the expected value of x, and you can find n moments about the origin. Now, let us look at this case. Consider the following scenario. Considering the following scenario, where I want to compare the, let us say the variation in heights of, let us say students who are in engineering in colleges versus students who are in high school. I want to look at the variability of, let us say the heights, or probably you can even take another scenario where in which I want to look at the variability of let us say age of students who are studying in college versus the students who are studying in school. So, let us take this. So, we want to compare the variability of of let us say heights of let us say students in let us say college with the heights, the variable with the heights of students in the height of students let us say in middle school. So, I want to make a comparison between this, or probably you could even put it at in I mean you can even take it another case where in which you want to compare the height of let us say adults and school going children, you could do whatever that is. So, I am just looking at this. Now, in this case we very clearly know that the heights of students in college would be much higher compared to that of the students in high school. So, we know that. So, what do? We say that okay, we know that, or it is obvious that the heights, or let us say heights of students in colleges are higher than the students in middle school, than that of the students in middle school. I mean what I am trying to say is like, look, on an average we already know that the students in colleges are taller than the students in the school. So, but I want to make a comparison, right. I want to make a comparison of the variability in heights. I mean you could have a maximum height in either cases. So, I do not want to get into this, but I just want to make a comparison of the variability. So, how do we go about doing this? In such a case, if we see for example if you look at the heights of let us say school students, heights of students in middle school, height of students in middle school is smaller or lesser than the is lesser than. So, forget about the absolute heights of the people in the group, but is less than the that of, that is exactly what I have written above also, that of the ones in college. Now, what does this mean? This simply means let us say the heights of middle school students to be HM and the heights of college going students to be HC. The average of these two guys are going to be at two different places. So, this guy average is going to be smaller, average is small than average of students, height of students in college. So, this is going to be smaller. So, if you want to make a comparison, it could be something like this. Say if I want to make a comparison between the two guys, so I might actually have some variation which is like this. This is basically the profile of heights of students let us say in the middle school, and I could have the heights of students in let us say in colleges could be something like this. This is nothing but heights of students in college. Now, there is no way that we can make comparison, because you see that okay, one, you know that the variability is something which you will not be able to talk about without bringing them to the same what do you call, bring them to the same mean. Okay. So, now what we do is I want to look at this, I want to look at x minus, let us say, the mean in each case. I want to make a comparison. So, what do? I would be able to do a better comparison if I had this HC, which is also centered somewhere here, which is like this, then I could say that look, or probably which is something like this instead of here. Suppose if it were to be like this, I would have had a better way of comparison. Say I would have told, okay, look, this variation is quite high, that is the spread of the random variable. Now, and this is the spread of this random variable Hm. So, this variation is quite small and that variation is quite high, provided if both of them were centered about the same point, but that is an easy way to compare. Now, when I do not have that, if I want to make a comparison, the easiest thing that I would do is I will at least try to bring both of them to be, both the distributions to be centered at the same point. The one way of doing this centering is subtract the mean of Hm from Hm and subtract the mean of Hc from Hc. Now, what you do is both of them would be centered at 0. So, you are mean centering it. So, what would we do is we basically look at this. So, what are we going to do? We want to look at expected value of, let us say, x minus mu. Now, there is a problem here. This expected value of x minus mu is going to give us a problem. Let us look at this. This is basically the average of values subtracted from the mean. I think I gave an example in the last lecture where I had, let us say, there are 3 values here, 1, 2 and 3. The average of this, the average is 2. So, what I would do is 1 minus 2, 2 minus 2, 3 minus 2. If I subtract, then the average of the above is going to be 0. That means it says that look, there is no deviation at all, average of the deviations is 0. That means you can straight away conclude that look, one of possible conclusions is saying that look, there had been no difference in the readings that you have taken, everything could have been 2, that is why this deviation is 0, but actually you will see that the sum of deviations is always 0. But I want to avoid this, therefore what I do is, you remember we had this squared error, we looked at expected value of x minus b the whole squared, we wanted to optimize that, we wanted to minimize that squared error. So, the same thing is what we want to do. I want to look at, instead of expected value of x minus mu, I will now look at x minus mu the whole squared, right. If I will look at expected value of x minus mu the whole squared, or I would look at now expected value of x minus mu the whole power n. This is basically what I call the nth moment about the mean, nth moment about the mean. And we also have another name for this, this is called the nth central moment. Nth central moment. And the second central moment that we have here, which is nothing but expected value of x minus mu the whole squared, this is basically what we call as variance of the random variable x, variance of x. This basically talks about the spread of x. This talks about the spread of x, and the square root of expected value of x minus mu the whole square is basically the positive square, it is basically what we call as standard deviation. So, the notation for the variance of x is given by variance of x is equal to sigma x squared. So, we have this to be the notation for our variance, and the standard deviation is given by square root of sigma x squared, which is sigma x, right. Okay. So, what is the central moments that you have seen, what is the use of the central moments? They basically they are location invariant. So, you want to look at the so basically the central moments allow quantification of properties of distributions in ways that are location invariant. Our mean expected value is a location. So, this is basically the location invariant. In fact, if you want to look at more details, much more detailed handling of the variance, you can look at this website, which is https gregory_anderson.com /blog/2020 . It is a nice article about this variance and moment. So, you could probably look at that. Now, what we will do is we will look at some of the interesting properties of the variance. We will look at some important properties of the variance now. Okay. So, properties of variance. The first thing that we would like to do is we will recall the formula for variance. We said that variance of x is equal to expected value of x minus e of x the whole square, which is nothing but expected value of x minus mu x the whole square, which is nothing but e of x squared minus 2 x mu x plus mu x squared. Now, by the property or the linearity property of the expected value operator, I can write this as expected value of x squared minus mu is a constant. So, I will take it as 2 mu x expected value of x plus expected value of this constant, which is nothing but the constant mu x squared itself. So, I am going to have expected value of x squared minus 2 times mu x, and e of x is again mu x. So, I have mu x squared plus mu x squared. Now, these two, one of them this minus 2 mu x squared plus mu x squared will become minus mu x squared, which implies expected variance of x, which is nothing but expected value of x minus mu x the whole square is nothing but expected value of x squared minus mu x squared, that is expected value of x squared minus e of x the whole square, right. So, that is basically the variance of x. So, what do we have? We have sigma x squared is equal to e of x squared minus e of x the whole square, right. So, this is basically the variance of x squared, variance of x. Now, the second one, the basically the property number 2, this is property number 1, which is basically the definition itself. Property number 2, I want to look at when will variance of x be 0. right. So, when will variance of x be 0? Variance of x is equal to 0. When can variance be 0? Variance is 0. I mean, what is it to say variance? There is some kind of change. Suppose I have all the values to be constant, there is no variation at all. So, the variation of a constant is 0. So, let me write this as variation or variance of b is equal to 0 for b a constant. Okay. Then third most important point is this: variance of a x is always a non-negative quantity. This implies it is non-negative. So, variance of x is always greater than or equal to 0. The fourth important property is this: suppose I want to look at this transforming a random variable x to y, variance of a x plus b. I want to look at this. I want to look at the variance of another random variable y, which is equal to a x plus b. That means a linear transformation that I am doing. So, y I am going to have y is equal to a x plus b. So, I want to look at variance of a x plus b. What is variance of a x plus b? Let us try doing that. So, this is nothing but expected value of a x plus b the whole square minus e of a x plus b the whole square, right. This is what I have. So, I have e of a x plus b the whole square minus e of a x plus b the whole square, the expected value of a x plus b the whole square. Now, it is easy to find out. So, what is this? This is equal to expected value of a square x square plus 2 a x b plus b square minus. So, this is nothing but e of a x plus b the whole square that we already saw. This is nothing but a e of x plus b the whole square. So, I have expected value of I will put all the apply the linearity property of this expected value and then get the value out. So, I am going to get a square e of x square plus 2 a b e of x plus b square, and this negative 1, this is going to be this term, the second term is going to be this. So, the second term is going to be, I am putting this subtraction here, this is nothing but a square e of x the whole square plus, there is a plus, so that will become a minus here. So, it is going to be minus 2 a b e of x, and then there is a minus b square, this negative multiplies that b square. So, we see that these two guys get knocked off, these two guys get knocked off. So, what I have is a square e of x square minus a square e of x the whole square, which is nothing but a squared into e of x squared minus e of x the whole square, and the term inside the bracket is basically the variance of x. So, I am going to get a square variance of x. So, what does this mean? So, here we have variance of a x plus b is equal to a squared variance of x. That means, if you add a constant to the data, it does not affect the variance, the mean gets changed, the mean gets added to b, or if you add if you want to look at e of a x plus b or e of x plus b, e of x plus b is nothing but e of x plus b. That means, the mean changes, but if for that constant that you have added, the variance of the resulting variable, which is nothing but let us say variance of x plus b, variance of x plus b is just going to be variance of x, because adding a constant is not going to change the variance at all. So, that is what we have. Okay. So, here let us look at something very interesting. So, what is it that we see here? We see that expected the E of x minus mu the whole square, this is basically the second moment about the mean, or the second central moment. This is related to the second moment about the origin minus mu x square in this way, right. It is related to this by this way. Okay. And most important property of this variance is basically the following. Let us look at this. Recall expected value of a x plus b was a times E of x plus b, and we also said expected value of x plus y is nothing but expected value of x plus expected value of y. This is what we have, right. Now, what we see is, if you look at, let us say, variance, if you look at a variance as an operator, now what I am going to have is, I want to look at this variance of, let us say, variance of g1 of x plus g2 of x. I want to figure out if this is equal to variance of g1 of x plus variance of g2 of x. I want to check whether if this is equal. So, I put a question mark there. So, we just want to take a simple example. Let us look at a simple case here. What is a simple case we are going to look at? I want to look at variance of, let us say, let both g1 of x and g2 of x be equal to x itself. Variance of x plus x, I want to look at this. So, what is this variance of x plus x is going to be? This is going to be expected value of x plus, so we already, okay, x plus x the whole square so let me take y is equal to x plus x, therefore I am going to have this as E of y squared minus E of y the whole square. This is what I have. This is nothing but E of x plus x the whole square minus E of x plus x the whole square. So, what do we have here? E of x squared plus 2 into x into x, so we have this plus x squared minus, let us say, E of x plus x the whole square. So, this is going to be mu x plus mu x the whole square. I will write this as, so this is going to be mu x plus mu x the whole square, which is nothing but E of 4x squared minus mu x squared plus 2 mu x squared plus mu x squared, which is nothing but E of 4x squared minus, let us take this to be 4 mu x squared, right. I have, which is nothing but this is nothing but 4 times variance of x, which is already available to us from that formula, which says variance of a x is a square variance of x. This is 4 times variance of x, whereas if it were to be a linear operator, it has to be variance of x plus variance of x 2 times variance of x. So, therefore, in general, let us write this, in general, In fact, you can even look at it this way, suppose if I take the expected value of x in this case to be 0, then all these guys will become 0, this is 0, this is 0. So, the entire term would be 4 times e of x squared. So, this is what we are going to have. So, in general, variance of g1 of x plus g2 of x is not equal to let me write this equal to variance of g1 of x plus variance of g2 of x is not true. This is the most important understanding that we have, right. Now, what we will do is let us quickly write down the variance for all those standard distributions that we had already looked at. So, we will be able to get a better picture. So, I want to look at Bernoulli distribution. So, I want to look at Bernoulli distribution where the we had x is Bernoulli of P distributed as Bernoulli of P. So, we have the variance of x in this case is expected value of x squared minus expected value of x the whole square. Now, this we already know, this is p squared and e of x squared is what we need to compute, this is e of x squared minus p squared. So, e of x squared is nothing but sigma 0 to 1 x into p x of x. So, I have 0 x squared. So, 0 squared into 1 minus p plus 1 squared into p. So, I have the following which is nothing but p. So, variance of x is equal to p minus p squared which is p into 1 minus p. So, the variance of x in case of Bernoulli distribution is p into 1 minus p. The other thing that we looked at was binomial. Of course, binomial you need to prove it, but then what you need to work out and then prove, but we will look at it in a very conceptual way. So, I am going to have binomial distribution where I am going to say x is binomial distribution or binomially distributed of parameter number of trials n and probability of success p, and we said this these are independent and identically distributed Bernoulli trials, identically distributed Bernoulli trials. So, we had for a single Bernoulli trial we had Bernoulli trial variance was p into 1 minus p. So, I am going to look at for n independent Bernoulli trials. So, for the key word is n independent, this is the key word n independent Bernoulli trials which is basically my binomial. So, the key word is independent. If it is not independent trials then we cannot do this. So, I am going to say only for n independent Bernoulli trials variance of x is equal to n times p into 1 minus p, right. So, for binomial case the variance is going to be n p into 1 minus p. Of course, you can find out the variance for your continuous distributions also. I will just leave that as a small task that you can complete. So, you can find out the variance of uniform distribution, geometric distribution, uniform then exponential Poisson distribution and so on. And others of course you can find out Poisson distribution, and yeah, probably you can even do for geometric. You can just do this as a task. So, you can obtain the values of variance for these random variables. Okay. In addition to this, we also have see, first thing we figured out the raw moments about some non-random value, which was expected value of x minus c the whole power k or n, and then we said that when we put c is equal to 0, we get the moments about the origin, and then we said that okay, I want to make a comparison, therefore the location is going to be different for, let us say, different distributions, but I want to look at the spread of all of them, putting them at the same location, in which case what we did is we subtracted the mean and then we looked at expected value of, let us say, x minus, instead of that c, the c value to be equal to mean itself. So, we said expected value of x minus mu the whole power n, we called them as the central moments or the nth central moment, and in that case what we found is the first central moment was 0, because the first central moment is nothing but expected value of x minus mu x the whole power 1, which is nothing but e of x minus e of x itself, which is 0. So, the first central moment was 0. The second central moment is what we called as variance, which was basically trying to tell us the spread of the random variable about the mean. This variance is basically spread, it tells about this spread of the random variable about the mean. In fact, if you remember when we did the when we found the expected value of x, we said that look, it is basically the center of mass, and we said in case of signals this is also the let us say the DC value present in a signal. Now, can we interpret it something similar to that in case of our variance? Of course, you can do. The squared quantity that you would look at it in terms of signals is basically the power. I mean, you will take it as like I squared r and v squared by r and so on. So, we have that. So, what happens is like in case of our variance, the variance happens to be a representation, or the variance is equivalent to the power in a signal. In fact, that is precisely why in most of your digital communication, or probably when you do your noise analysis in communication systems, you would always have this which says like additive white Gaussian noise with 0 mean and unit variance, and that is what you will use to compute the signal to noise ratio. You will talk about signal power, and noise power you will talk in terms of noise variance you talk. So, the variance is going to be equivalent to the power in a signal, right. So, we have all that. Of course, you can look at any other higher order moments, and once you collect all these moments, even then, I mean, all these moments would actually help you characterize or describe the random variable mean. So, what did we have in the beginning? We said that we had the density function or the mass function, probability density function or the probability mass function, which was an exact representative of the random variable. Then we said we could have cumulative distribution function, which is also a representative or representation for the random variable. Then we said that we need a typical value. We need a typical value among the set of all the values of the random variable. That is where we got into the idea of expected value of x and the average, and we also wanted to look at the spread, which we talk in terms of variance. You can look at any other higher moments, expected value of x power 70, you can look at expected value of x minus mu the whole power 23, you can look at all the infinite moments that you have. Once you get that, the random variable is also, you say that the random variable is also described by the moments that you have. Is there a way to easily compute the moments? Like you have what is called as a moment generating function, which I would probably not be doing right now. If I can come back to it at a later point of time, I will do it. But as of now, what we will do is we will wind up our insights about single random variable, because most of the times random phenomena exists, you have multiple random variables to be there together. I mean a good example is like, say, I mean, as an individual, you might have seen a kid has its own behavior at home and another kid has its own behavior. Now when these two kids join together like they are friends, their joint behavior is going to be something different. Now we want to look at this joint behavior, like, is the behavior of one kid going to influence the behavior of the other, or are they independent, are they not going to be kind of influencing the other. A good question to ask is like, when the petroleum product price increases, you find that the essential commodities cost also increases. That means the cost of the petroleum products is going to be a random variable and the cost of essential commodities is another random variable. Therefore you find one of them to influence the other. So what we want to do is we want to study this joint behavior of random variables, and that is what would be the focus of the next week's lecture. We are going to look at jointly distributed random variables, and we are going to look at the joint moments and so on. Namaste.